had unfortunately visa issues and couldn't make it. So we're going to take the opportunity to have a meta situation talking about artificial-based game testing, basically, by having an artificial presentation. Yeah, and I'll let Perttu take the stage. Welcome, Perttu.
And welcome to this Hi video talk. The basic problem discussed in this paper is that playtesting is expensive. Recruiting players to a lab is a hassle. Online experiments can be easier, but there's still a substantial cost if one needs to gather large-scale analytics. The question many seem to be asking right now is whether one could use AI players to automatically generate data about player behavior and experience. Ultimately, this could enable automating parts of the game design, or even whole game design. For example, one could have an optimizer, in this case operating on some game design parameters, that define the game played by simulated players, and the players then generate behavioral and player experience data. This data can be compared against some targets, here defined by a game designer, and this then results in a score that the optimizer tries to maximize through iterating the design parameters. If this sounds like science fiction, I should stress that it's by no means a new idea, and various experiments already exist, such as this seminal paper from 2008. The topic is hot now because the scope of games that can be played or solved by AI has experienced a sudden explosive growth. If you haven't been living under a rock, you probably know that just 3 years ago, DeepMind showed that it's possible to beat humans in many classic games using deep reinforcement learning. This new and exciting here was that thanks to the power of deep neural networks, the AI was able to use raw pixel data as input, without any game-specific information. Reinforcement learning is conceptually very simple yet powerful. Basically, the agent at first simply explores random actions. It then gradually learns to repeat actions that yield high rewards. In later work, deep reinforcement learning has been proven powerful, especially if combined with traditional planning and search techniques like Monte Carlo tree search. Multiplayer games with hidden info still present challenges, but research is advancing at a staggering pace, and OpenAI's Dota AI can already beat top players at least in a 1 versus 1 setting. The field is pushed forward by annual AI competitions in a variety of games, such as Doom. With such AI, one can start probing questions that have traditionally required human playtesting. For example, AI can test that the level can be completed, and it can also reveal possible exploits that the designer did not anticipate. AI characters are actually notoriously good at this. For example, it's quite hard to get them to walk in a natural manner, as they can easily discover alternative gates, like here on the right. When I've discussed AI playtesting with game companies, this has been seen as a great asset. There's actually a super interesting paper fresh in archive that collects together examples of such artificial creativity. If AI can discover optimal playing strategies, timings, and placements, it also means that it can be used for analyzing game balance. For example, generating reports of which characters win when pitted against others. The main limitation of reinforcement learning and other AI methods is that they are basically all some form of optimization. They work well as long as there's some explicit reward signal that the agents try to maximize. For example, a game score or level completion bonus. However, many games are much more than simply competing or solving problems to get rewards, Minecraft being a prime example. This is why we also need AI that models human motivation and emotion, which should allow the emergence of things like social sandbox play. So, modeling of motivation of simulated players is what we focused on in this paper. It's a young, emerging field with somewhat scattered results, and we thought it's time to do a review to guide future work. Human-like simulated players for playtesting is basically my doctoral student Shaghayegh's thesis topic, and this is her first paper. However, she's from Iran and did not get the Canadian visa in time, despite applying right after getting the acceptance notice. In this paper, we first review psychology of intrinsic motivation, then review how it has been implemented in AI. In these two steps, we had help from some previous reviews. This gave us keywords that we then used to systematically search for papers that model intrinsic motivation in the context of games. Here's the searches that we conducted. The exclusion criteria are explained in the paper. For example, we excluded many papers that did not have any game-playing agents, but instead focused on psychometric models of human players. Table 2 of the paper summarizes the results following the three-part approach. On the left, we list central intrinsic motivation components. The middle column then lists examples of their applications and implementations in AI. On the right, we summarize the papers we found in player modeling and game-playing agents. Let's now review some basics of motivation psychology. First, one should note that things like a game score or level completion reward are considered as so-called extrinsic or external motivators or rewards. Maximizing these is where AI traditionally excels at. At the heart of it, all AI is basically some form of optimization. What about sandbox play? Such play can have no extrinsic rewards but still be very motivating. In psychological literature, intrinsic motivation is defined exactly as that. This is predominantly explained through the satisfaction of basic psychological needs. Self-determination theory is perhaps the most popular intrinsic motivation theory. It posits three central intrinsic motivations: the needs for feelings of competence, autonomy, and social relatedness. Self-determination theory has also been validated in numerous other fields, such as education and sports. Personally, I've done a lot of work on exogames that boost the players' movement abilities, giving them superhero experiences. Later on, self-determination theory has given me an explanation why this is so powerful, as it can be considered to elevate one's perceived competence and also autonomy. We've also demonstrated how technological augmentation can transform a solo sport into social play. Specific to games, there are several papers on both motivation components and player typologies. In effect, the typologies present categorizations or subdivisions of the space of motivations, for example, based on the strongest motivations, which vary between players. Although each dataset from a different game can provide a somewhat different categorization or different motivation factors, on average, constructs similar to self-determination theory seem to be prevalent. Interestingly, this seminal paper by Sheldon gets around the problem of dataset specificity. They simply prime the participants by asking them to think of the single most satisfying event of the past month of their lives. The participants then rated their agreement about claims such as, "During this event, I felt close and connected with other people who are important to me." Interestingly, even with such a general setup, self-determination theory's constructs emerged in the top 4 salient needs. On the 5th place, note that there's a pleasure stimulation construct that consists of items such as experiencing new sensations and activities. This is an evaluation of novelty of the experience. Novelty, on the other hand, is crucial to curiosity, which is the 4th major intrinsic motivation we discuss in this paper. Curiosity also provides a link between motivation and emotion from the point of view of so-called appraisal theory. According to the theory, emotions are elicited through appraisals or evaluations of variables of personal significance. For example, Sylvia's work on curious interest suggests an appraisal structure of novelty, complexity, and comprehensibility. In games, the importance of curiosity was highlighted already in Malone's early work on educational games. So, how about intrinsic motivation in AI? As in many other AI topics, some of the basic foundation was laid by Jürgen Schmidhuber already back in '91. The paper was about curiosity, and the field has since expanded to other intrinsic motivations, such as competence. self-determination theory appears influential on AI side too. So, how does it work? As I said earlier, all AI is basically optimization, so we need some kind of a reward even in intrinsically motivated AI. The dominating paradigm seems to be that one first considers the case without explicit rewards, which may or may not be included in the observation here. Then the model is augmented with an extra module. This module deals with motivation and emotion and outputs a so-called intrinsic reinforcement signal or intrinsic reward. This is what the optimizer then maximizes. For example, artificial curiosity can be implemented by giving an intrinsic reward for exploring actions with unpredictable results. As the agent learns to predict the results, it then moves on to new actions. There are also other formulations of novelty, such as counting how many times a state has been visited, or the same stimuli have been observed. This is powerful, especially in games where the agent would have to do a lot of random exploration to reach any extrinsic rewards. One such game that DeepMind's initial deep reinforcement learning could not solve is Montezuma's Revenge. As it says on the video, a traditional randomly exploring reinforcement learning agent will practically never get far in the game. However, a curious agent avoids repeating the same mistakes and eventually solves the game. Expanding beyond curiosity, AI systems can use various need satisfaction signals or positive emotions as the intrinsic reward. The models of emotions utilized are more or less based on appraisal theory, depending on computational appraisals, such as the estimation of novelty. If you are interested in learning more about computational models of emotion, this survey is a good place to start. So, what appraisals and motivations can one implement computationally? I think one gets a pretty good intuition of this by looking at the questionnaire items used to measure motivation and emotion in humans. For example, competence is fairly straightforward to operationalize, as many AI methods produce not just solutions to a problem, but also estimates of problem difficulty. Like I already said, curiosity and novelty-related measurements are also fairly straightforward and common. Social relatedness is harder, for example, thinking of this kind of item. But there are some experiments that keep track of the number of interactions between agents and whether the agents reciprocate, for example, in helping or gifting behaviors. However, looking at this item from Sheldon's autonomy scale, I'm baffled. Likewise, it's very hard to implement computationally. The same goes for this self-actualization item, again from Sheldon. Considering this, it's perhaps no surprise that AI also uses computational appraisals or metrics that do not have exact counterparts in psychometrics. An example of such metric is information theoretical empowerment. Roughly, this means how large effects the agent's actions have on its sensory inputs. Finally, we get to the systematic review part. Of course, I only have time to go through some examples. Again, we conducted literature searches with keywords from the psychological and AI literature, such as intrinsic motivation, competence, curiosity, and combined these with player modeling, player experience, and game testing. We had to exclude many papers that did not have any game-playing agents, but instead focused on questionnaire data from human players. However, we still found some papers, here shown for competence and other related computational appraisals. For example, Merrick implemented competence motivation by driving the agent to practice actions with medium predictor error for utility. Thus, the agent avoids actions and states where it can predict utility either very accurately or very inaccurately. In the same paper, Merrick implemented curious interest using an inverted U function of novelty. Novelty was in this case not computed based on prediction error, but using Stanley's model of neural habituation that dates back to 1975, published in Nature. Like I said previously, implementing social relatedness motivations is less straightforward, but my co-author Christian has done some work on that. In this case, the agents try to maximize both its own empowerment and that of others. More recently, computational measures of empowerment of AI agents have also been shown to have some predictive power for human player experience. In summary, various motivation models exist. People have used especially curiosity, competence, and empowerment. And there's less work on the more computationally difficult ones, such as social relatedness. The motivation models are still quite simple, and moreover, they are not typically validated with real player data. In the future, we need to validate and fine-tune the models based on human player data. However, for this, we also need better datasets, such as datasets with synchronous play traces and emotion and motivation measurements. In my group, we are looking into facial expressions, into sort of generating AI Let's Play videos with human-like reactions to game events, which then could be compared to real humans. We are also preparing a study about how far the industry is in adopting AI-based testing, what challenges they have faced, and what benefits they have reaped. That was all. Thanks for your attention. Of course, I'm not there for questions, but feel free to contact me or any of the co-authors with questions, comments, or collaborations.
All right, to clap or not to clap?